Question 1. The synthesis of ammonia and H3 is carried out by the Haber process, which is this reaction. And this reaction is an exothermic reaction. It releases heat. And the question was, which of the following conditions are required to increase the yield of ammonia? So by increasing the yield of ammonia, we mean increase the amount of product, which is the NH3. So we want the reaction to shift to the right. Now, the addition of a catalyst, the first option is incorrect because the catalyst speeds up the forward and the reverse reaction. So it's not going to increase the yield of ammonia. It doesn't have any effect on the concentration or the equilibrium concentration. Now, increasing temperature, if we increase the temperature, let's suppose this is the delta H, and since it's an exothermic reaction, so I'm going to put delta H on this side. So if delta H is on the product side, and if we increase the temperature, then delta H is going to increase. And so the system will counteract this change by shifting towards the left side. And by shifting toward the left side, this means that the NH3 is going to decrease. So the yield is going to decrease. So this is false and this is false. Now removing nitrogen, if we remove nitrogen, so nitrogen is decreasing. Now the system wants to counteract this change and increase N2. And so in this case, the system is going to shift also to the left. So the amount of NH3 is going to decrease. So this is also false. Now removing ammonia, if we remove ammonia, then this means that we are decreasing the amount of ammonia. So the system is going to counteract this change and make the reaction shift to the right side. And in this case, the NH3 is going to increase, and so the yield is going to increase. So this option is correct. Now, increasing the pressure, if we increase the pressure, the system wants to decrease the pressure by shifting toward the side in which we have less moles of gas. And nitrogen is a gas, hydrogen is a gas, and NH3 is a gas. And here we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. Now when we increase the pressure, the system wants to go towards the side where we have less moles of gas to decrease the pressure. So it's going to go towards the NH3, and in this case we're going to have more NH3 and the yield is going to increase. So the only correct option, or the only correct conditions that increase the yield of ammonia, are removing ammonia by condensing it to liquid and increasing the pressure. Question 2. The synthesis of sulfuric acid is carried out by the contact process. The main equilibrium reaction involved is this reaction, in which I have 2 moles of sulfur dioxide reacting with 1 mole of oxygen to give 2 moles of sulfur trioxide. And this reaction is exothermic as delta H is on the product side. Now, to get the best yield of sulfur trioxide, and this is sulfur trioxide, so to get a higher amount of sulfur trioxide, we need to do something with the pressure. We either need to decrease the pressure or we need to increase the pressure to shift the equilibrium position toward this side. Now, if we increase the pressure, then the system is going to decrease it by shifting towards the less moles of gas. And here I have 3 moles of gas, whereas over here I have 2 moles of gas. So in this case, I need to increase the pressure in order to make the system shift towards where I have fewer moles of gas, and therefore shifting the reaction towards the right. Now, there's also another thing that we can do in order to make the reaction shift to the right, and this is by decreasing the temperature. Because if we decrease the temperature, then the system is going to increase the temperature by shifting toward this side in order to increase delta H again. So as I decrease the temperature, delta H will decrease, and so the system will try to increase delta H again by shifting towards this side. So if we also decrease the temperature, then the system is going to shift to the side that releases energy. which is this side. Question 3, we have this reaction taking place, this reversible reaction, where we have 1 mole of nitrogen reacting with 3 moles of hydrogen to give 2 moles of ammonia. And it's an exothermic reaction. And the question was, to increase the yield of production of ammonia, should we use a high or a low temperature? And should we use a high or a low pressure? Now, to solve the first part, which is about the temperature, I need to place the delta H over here on the right side, and this is because it is an exothermic reaction, so I need to place the delta H as a product. Now, to make the reaction produce more ammonia, I need, of course, to decrease the temperature, because as we decrease the temperature, the system is going to increase the delta H. Is going to go to the side that will produce energy in order to increase the delta H again. So first I have to use a low temperature, and for the pressure I need to check the number of moles on each side. So on this side I have 4 moles of gas, and on this side I have 2 moles of gas on the product side. Now I need the reaction to shift in the direction that will produce less moles of gas in order to get more NH3. Therefore, I need to use a high pressure, because as we use a high pressure, the system will decrease the pressure by shifting towards the less moles of gas. So it's going to shift towards the 2 moles. Now for question 4, we have this reaction again, and the Haber process is conducted at a temperature of 450 degrees Celsius and a pressure that's between 203 and 405 Pascal. Now, which of the following are true about the process? So let's look at each option. High temperature increases the yield of the reaction. Now this is false, because if you use high temperature, as we said before, the delta H is going to increase. System wants to decrease delta H, which is on the product side, and it's going to shift toward this direction. So it's not going to increase the yield, as because the ammonia is going to decrease. High temperature increases the rate of the reaction. This is correct, because if we use high temperature, then we would have the molecules will have more kinetic energy. Now let's go for the third one. So in the third one we have low pressure increases the yield of the reaction. So if we use a low pressure, then the system is going to increase the pressure by shifting to the side in which I have more moles of gas. So let's see, where do we have more moles of gas? Here I have 4 moles of gas, and here I have 2. So the system is going to shift to the left and decreasing the yield of ammonia. So this is false. Now, the last option is high pressure is dangerous and expensive. This is true, as we need more advanced equipment if we are going to use a high pressure, and it's also at the same time it is dangerous. So the only correct option is this one and this one. Question 5. Ammonia is an essential raw material in many industries. For example, it's used in the production of fertilizers such as ammonium nitrate and H4NO3. Now, they said calculate the percentage of nitrogen in ammonium nitrate and give your answer to two significant figures. So, to find the percentage of nitrogen, we're going to use this formula: atomic mass of the element times the number of atoms for this element over the molar mass of the compound. Now the atomic mass for nitrogen is 14, and we have 2 nitrogen atoms. We have this N over here and this N over here. So we're going to multiply it by 2. And the total molar mass, I forgot to write over here, times 100. And the total molar mass is 80 for the whole compound NH4NO3 times 100. And so the answer is going to be 35%. Ammonium nitrate is produced by reacting aqueous ammonia with aqueous nitric acid, Write the chemical equation of this reaction and include state symbols. So aqueous ammonia is NH3, and this is the state symbol for ammonia, and it's reacting with nitric acid, which is HNO3 aqueous, and it's going to give NH4NO3, which is also aqueous. This is the reaction with the state symbols. Now, in the next question, they said, consider a reaction in which nitrogen, hydrogen, and ammonia gases are present at equilibrium in a closed vessel. Choose in which direction you expect the equilibrium position to shift upon each of the following changes. Now, if we are going to add more nitrogen, so increase nitrogen, system wants to decrease it, and to decrease the nitrogen is going to shift to the right. So we're going to write the equilibrium position shifts to the right. Now some ammonia is removed, so if you remove ammonia, ammonia is going to decrease. System wants to increase it again by shifting in its direction. That produces the ammonia, so it's going to shift to the right. So we have the same answer for as above. So it's also going to shift to the right. Now, if more Fe is added, and Fe is actually a catalyst, then the equilibrium position is not going to be affected since it's a catalyst, and the catalyst speeds the forward reaction and the reverse reaction at the same time. So I'm going to write over here the equilibrium position will not change, as catalysts do not have any effect on the equilibrium position. Now, if the temperature of the vessel is increased, so this is an exothermic reaction, delta H is on the product side. If we increase delta H, so the system is going to decrease delta H by shifting towards the opposite direction, which is the left side. So I'm going to write over here left. And if the pressure is lowered, the equilibrium position is going to shift in the direction in which we have, let's first look at if the pressure is lowered. So if the pressure is lowered, then the system wants to increase the pressure, and to increase the pressure, it's going to go towards the side in which I have more moles of gas. So over here I have 4 moles of gas, here I have 2 moles, so it's going to go towards the side in which I have more moles, so it's going to go to also towards the left. So this answer is also left. Now question 6, 5.2 mole of NaOCl is introduced in a 2-liter closed container and allowed to reach equilibrium. They said consider the following reversible reaction, and we need to write the expression for the equilibrium constant Kc. Now for Kc, we're going to use concentration, and for Kp, we're going to use pressure. So if I want to write the equilibrium constant Kc, it's going to be product, which are Cl2 multiplied by NO divided by NaOCl, and we need to raise them to their coefficient. Now Cl2 is 1, NO is to the power of 2, since I have this coefficient over here. The same for NaOCl, since I have a coefficient of 2, so it's also going to be raised to the power of 2. Now the second question, they said calculate the equilibrium concentration if the equilibrium concentration of NO is equal to 0.059 mole decimeter dm minus 3. Give your answer to 3 significant figures. So to solve this question, I need, of course, to use an ice table. So the reaction taking place is 2NaOCl gas and reversible arrows, and I'm going to write 2NO gas plus Cl2 gas. And here I'm going to put ICE. Now let's first find the initial concentration for the NaOCl. So they said over here that I have 5.2 moles in a 2-liter closed container. So I can use the formula, which is N equals C times V, to find the initial concentration for NaOCl. So to find the initial concentration, C is equal to N over V, and it's going to be equal to 5.2 over 2, and it's going to be equal to 2.6 M. So I'm going to put over here 2.6 M, and here I'm going to put 0, 0, as nothing was stated at the beginning if NO or Cl2 are present. There's only NOCl. Then I'm going to put over here minus 2x. I'm going to put plus 2x over here and plus x. Since the reaction is going to shift toward this side as I have a 0 over here. So of course these are going to increase. So I'm going to put positive on the product and negative on the reactant. And I'm also going to take into consideration the coefficient. Next, I'm going to put 2.6 minus 2x, 2x over here, and then x. And one thing they said is that the equilibrium concentration of NO is equal to 0.059. So this is NO, and here we have equilibrium. So the equilibrium concentration 2x is going to be equal to 0.059. So I'm going to put 2x is equal to 0.059, and x is going to be equal to 0.0295. Now I can find the equilibrium concentration for Cl2 using the x value. So for Cl2, it's going to be equal to 0.0295. And for NOCl, if I substitute by x, then I'm going to get a value of 2.541. And since they need the answer to three significant figures, so it's going to be 2.454 m. And for this one, it's going to be 0.0295 m. Now for part 3, now for number 3, they said calculate the value of Kc and give your answer in scientific notation to three significant figures. So now since I have the values for the equilibrium concentration, I'm going to use the expression for Kc, which is Cl2 times NO2 squared over NOCl squared, and I'm going to substitute by the values that I got in number 2, which is 0.0295 for Cl2, 0.059 squared for NO squared, and I have 2.54 squared for NOCl. And the answer is going to be 1.59 times 10 to the power of minus 5. And they said in the final answer that our final answer needs to be to three significant figures and in scientific notation. So this is the final answer. Question 7, we have the following reversible reaction taking place. 12.5% of the moles of SO2Cl2 introduced initially decompose to reach equilibrium where the total pressure is 0.9 atm. Use the following to label the partial pressures for SO2Cl2. So for SO2Cl2 it's going to be P1, for SO2 it's going to be P2, and for Cl2 it's going to be P3. And they said write the expression of the equilibrium constant Kp. Now Kp is going to be products over the reactants. So it's going to be the pressure of SO2 times the pressure of Cl2. And since the coefficient is 1, so there's no power in this case. And over the pressure of SO2 Cl2. So we're going to substitute by the labels that they gave us over here for the partial pressure. And it's going to be P2 times P3 over P1. This is the expression for Kp in which we use the partial pressure. Now they said calculate the equilibrium pressure of each species and give your answers to three significant figures. Now of course to solve this question I need to set an ice table, the same as we did in the previous question. However, we're going to use pressure and we're going to find the equilibrium pressure and find our answers to three significant figures. So let's start with the ice table. So SO2Cl2, I'm going to write the reaction again. It's going to give SO2 plus Cl2 ICE. Now instead of using the number of moles as we did before, where we have 12.5% of the moles of SO2Cl2 introduced initially, I'm going to work over here with the pressure. And why am I able to work with pressure? Because over here we're working with gases, and we need to suppose that we have a constant volume and temperature. And as you know, PV is equal to nRT. And since we have these are all constants, so the pressure is going to be directly proportional to the number of moles when I'm working with gases. So I can work with pressure in the ice table, and I need to work with pressure since I'm going to be finding the partial pressure for the or the equilibrium pressure for each of the species given. So the first one is going to be P0 because I have this is the initial pressure that I have. Let's say you can think of it as the initial number of moles that I have for SO2Cl2. And here I'm going to put 0 and 0. Then I have 12.5% of the moles of SO2Cl2, they decomposed. So I'm going to put minus over here, and there I'm going to put plus and plus. And over here I'm going to put minus 0.125 P0. Now why did I do this? Because 12.5% if I divided by 100, then it's going to be 0.125. And 0.125 of the moles, which I can say over here of the initial pressure, has decomposed. So I can work with the pressure instead of moles, and I can say minus 0.125 times the initial pressure decomposed. And then I'm going to put over here, since we have plus x over here, so it's also going to be plus 0.125 b0 and plus 0.125 b0. Now this is because I suppose that x is going to be equal to 0.125 b0. So let's say if you're working with the x, you would have placed over here a minus x, a plus x, and a plus x. Now since you know that this is the amount that decomposed, so you can think of it as the x value that I placed, because this is what they mentioned over here. So let's solve this ice table. So I'm going to put the values over here. So it's going to be P0 minus 0.125 P0. Then over here I'm going to put 0.125 P0, and here I'm going to put 0.125 P0. Then since they said that the total pressure is going to be 0.9, so I have to find the initial pressure, and I'm going to add the values. All of these values, I'm going to add them and make them equal to the equilibrium pressure that was given, which is 0.9. So I'm going to put P0 minus 0.125 P0 plus 0.125 P0 plus 0.125 P0, and it's going to be equal to the total pressure, which is 0.9. And working this out, I'm going to get an initial pressure of 0.8 atm. So now I can substitute by P0 to get the values for the equilibrium pressure. So the initial pressure is 0.8. Therefore, I can now find the pressure for SO2Cl2. So the pressure for SO2Cl2 is equal to 0.8 minus 0.125 times 0.8, and we're going to get a value of 0.7 atm. Now since they need the answer to three significant figures, so I'm going to add the necessary zeros over here. Now the pressure of Cl2 is equal to the pressure of SO2. It's equal to 0.125 times 0.8, and this is because I'm substituting the P0 by 0.8. I'm multiplying it by 0.125, same as I did over here as I substituted P0 by the initial pressure by 0.8. And so the pressure of Cl2 is going to be equal to the pressure of SO2, and it's going to be equal to 0.100 atm to make them three significant figures as required by the question. Now the final question was calculate the equilibrium constant Kp and give your answer in scientific notation to three significant figures. So over here Kp is equal to the pressure of SO2 times the pressure of Cl2 over the pressure of SO2 Cl2. And since we got the values for each one of them as 0.1, so I'm going to put 0.1 times 0.1, so it's going to be 0.1 squared over the 0.7, and we're going to get a value of 0.014285. Now they need the answer in scientific notation, So it's going to be 1.4285 multiplied by 10 to the power of minus 2, since they need the answer to three significant figures. So I'm going to count 1, 2, 3. After the 2, I have 8. 8 is greater than 5, so the final answer is going to be 1.43 times 10 to the power of minus 2, and this is the value of Kp.